We've run a study, we've run a simulation. We found that the simulation in the first cut didn't come up with the same lift to drag coefficient ratio that we expected. We were expecting a ratio of something like 40, um, and we got something like 4. So clearly we have a problem. So let's look more carefully at this simulation approach and see what we can learn from it, and then see if we can change the simulation parameters to make it more realistic. So the way we're going to compare our results is going back to the NACA data, and you'll see that um, there are plots of the lift coefficient and drag coefficient. Now, I already have calculated the Reynolds number for this, and I know that my Reynolds number is around 250,000. And these NACA data plots are for particular Reynolds numbers. So I'm just going to turn off all but the 200,000 Reynolds number data. And from that, I can see, better update the plots. There we go. So you can see that I've got this data coming from the source of the airfoil, and this data comes from primarily wind tunnel testing. And so the wind tunnel tests that were done for this airfoil and others are a pretty accurate prediction of what you would expect in the most simple ideal case. So what we should do is compare this result with what we've just calculated from our model. Now, I've already done several runs like this, and what I ended up producing was an Excel spreadsheet which compares my runs at multiple angles of attack with the data that I got from the airfoil website. And so let's compare and see how close I was able to get to that proper result. Now, first of all, I downloaded from that airfoil website the lift coefficient over here and the drag coefficient data, and I calculated a lift coefficient divided by drag coefficient. So basically, I used their data to reproduce the actual plots. And from that data, here's what I calculated. Now, the lift coefficient is here, and that looks exactly like what we would expect. The lift coefficient for a simple airfoil goes from 0 at 0 angle of attack. There's no lift when a symmetrical airfoil is pointing straight at the wind. Up to a maximum around about 10 degrees, which was the angle that I was using in the simulation. And then it starts to get flow separation and breaks off after that point. Similarly, the drag coefficient from the data shows the drag starts out at some non-zero value. There's definitely drag on an airfoil pointing into the wind. And as the airfoil tips upwards, the drag coefficient increases. Similarly, if you take those two coefficients, lift and drag, and divide one with the other, you can find that there's an optimum lift over drag interval somewhere around, in this case, 4 or 5 degrees, where if you have a higher angle of attack than that, you're getting more drag than you are lift out of the airfoil. And so your most efficient use of the airfoil is at that angle. Now let's compare that to what our simulation showed. The simulations, when I ran them at 0, 2.5, 5, 10, 15, and even 20 degrees, they actually showed quite a similar, when I went through the calculation using a half rho v squared as the factor that you multiply the drag coefficient by to get the force. I found that the drag coefficient was pretty close. You know, not perfect beyond 10 degrees, but then the data really isn't very good beyond 10 degrees. So who's to say? This could be right, it could be wrong. The lift coefficient, on the other hand, is totally wonky. taking the numbers that I used, that lift coefficient is much lower than I should have expected. And so basically my, my model that I created after running it, I did a reasonable prediction of the skin friction, so the friction drag, which you would expect because that's a simple turbulence model, but the effect of lift, which is caused by the boundary layer and circulation, wasn't very well modeled. So that's kind of interesting. Now, if you go through more of this, you'll find that a couple of the problems with this model are the way I laid it out here is the calculation domain is not ideal for this. If I just look at the side, then you can see that, let me just turn off, I want to turn off the grid, hide the grid, and I think I'll change my cut plot so you can see the numbers better. And so you can see from this that my model domain up here, there's still something going on up at the top of this domain. And there's still something going on down here. Well, the fact that that domain is so small has an error or produces an error in the result because the simulation isn't really knowing what happens outside of those boundaries. So that creates a problem when you go and try and calculate some fairly derived numbers like the force on something like this. So that's a problem. So I could improve this model if I increase the size of my computational domain. So if I drag this up, and typically you're going to want to have this something on the order of 5 times the chord. So if the chord of this is 1 meter, then you want at least 5 meters up and 5 meters down. And you're also going to want to have something like 10 times the chord downstream and maybe 5 upstream. And you certainly can play around with those things, but if your calculation domain isn't something like this, then you're asking for trouble in terms of the accuracy of the results. So there's the problem. If we tried to then rerun this simulation with a domain this size, then the time it will take to solve will be hugely different because we've just created a whole lot more grid points, and that's going to cause a real problem. So one way that we could improve things is, do we really have to have the calculation domain the full length of the airfoil? Could we just do this? In fact, could we make it so thin that it becomes a two-dimensional model? So if you edit the definition for the computational domain, you'll see that one option is to do a 2D simulation. And my 2D simulation will be in the XY plane. So now my simulation domain is just that. And if I go back to my show the mesh, you can see that I've refined the mesh as it needs to for the simulation. And I've got relatively fine points in here. Now that I've got so fewer points, I could actually make some refinement in there. So I'm going to make a local mesh, and I'm going to make a local mesh around that body, and I'm going to refine. I'm going to refine more of the cells. Now if I run again, you'll see it's running through much faster because I don't have a whole lot of that three-dimensional space that's really a waste of time to simulate. And I've distributed the grid in a much more efficient way. And I still reach the maximum 100 iterations. If I look at a plot of my goals, see how they look. And there's definitely a whole lot of wiggling around here. And that doesn't look too good. So I'm not really optimistic that the Y-force has worked very well in this. Let's see what the plot looks. First of all, let's see what the mesh looks like. And you can see that our mesh is quite fine close to the body, and it gets much bigger further away, which is reasonable. Maybe that's too much bigger further away, and that could be a problem. Let's see what our flow lines look like. And they look interesting. So they're showing that I'm getting a lot of these vortices breaking from the airfoil. And so that would be separation. If I look at the flow trajectories, that will be interesting. And you can see from them as well. I'll just turn that off. You can see from these as well that there's nice even flow on the bottom side, the high pressure side, but on the back side, there's this separation bubble. And well, that's interesting to look at. Looks kind of cool. We have no idea whether that's real because this airfoil, it is only at 10 degrees and doesn't seem like that's the behavior we'd expect. But again, we can take the results of the forces, and we had an x component of 0.13 and a y component of 0.025. So here with this simulation, as I've changed it, we now have more drag as compared to the lift. And the numbers are irrelevant. They just are different because of the two-dimensional model made a smaller surface area. If I compare that to these graphs of lift and drag, or to my own lift and drag data, my own plots, at 10 degrees, I should be seeing a lot of lift as compared to the drag. And that simulation showed something different. And you could see from the way it was not converging that there was something going on. Now, this is the real challenge with flow simulations. So this has been an interesting story in the end, because what we've just seen is I imported the geometry from a real airfoil, and I fixed it up and made a solid model of it, and it looked like an airfoil. And then I ran what I expected would be realistic simulations. I had lots of grid points. I did a three-dimensional simulation, and it was sort of like the real world. And certainly if you probed more deeply, as I did not on camera, at the plots of the different velocity fields at different angles of attack, they look kind of cool. They look realistic. In fact, you can predict the point of separation on the backside of the airfoil. That's sort of consistent with the real data, but when it comes down to looking at the actual numbers of forces, they don't match the real world very well. Now, it's not that they can't. The problem is they don't. And if all you do is look at the pretty colored pictures, you won't know that the simulation is not simulating the real world very well. That is the problem with flow simulation. The only way to prove that this model is working properly is to compare with something real. And the only way to make it work properly in the end is to apply the right grid, that it's fine enough where it has to be fine, that it's broken down in the right way with the right elements, that the surface boundary layer is modeled properly with the proper turbulence parameters. A lot of stuff to think about. And so every time you do this, as you saw, the solution has to go through iterations because, as I explained in the previous video, it's solving the finite volume method, and there isn't a closed form single matrix inversion that gives you all the algebraic equations that you can then solve. The solution has to help formulate the algebraic equations to make everything add up. So it's great to make pretty colored pictures, but don't trust them until you have proved that they're working right. Everything I've just shown you gave results in streamlines that look just like your fluids textbook, but they weren't right. So that's where we'll stop for now. And we'll talk about getting you trying some simulations of your own with this in the next video.